So I'm going to talk about 10 years of Spitzer moving high redshift from redshift of zero point 0.5 to redshift of 10. And any of you who've written this Spitzer proposal for extragalactic will recognize the humor in this, that when Spitzer first launched, high redshift was defined at zero point 0.5, and we very quickly exceeded that. So at launch, as I said, it was thought that Spitzer would be studying high redshift galaxies at zero point 0.5, and this was very quickly exceeded. In the first year, we got out to redshift of 4, and as I'll show, we're now out to redshift of 10, and I'd say we haven't hit the redshift limit yet. We're likely going to detect even higher redshift galaxies in the near future once we know how to find them. And what follows is a tour of highlights of what Spitzer has done in the past, what it's currently doing, and what it will do in the future, based on the work that I've been doing and a poll of luminaries in the community. So one of the first things Spitzer did, and most important things, is conclusively measure the global star formation history to a redshift of 3. We know that in the local universe, most star formation is heavily obscured. And before Spitzer, we had few constraints on how this obscured star formation was distributed by galaxy luminosity and by redshift. And so this is an example of one of the first measurements of the so-called galaxy luminosity function, or how the obscure star formation is distributed by galaxy luminosity, measured by Emmerich Laflock. There's similar work by Karina Caputi. And it shows that as soon as Spitzer launched, we were able to measure this to a redshift of 1.3. And the only reason we didn't go to higher redshift right away is that we didn't know how to bridge the redshift desert and get redshifts of galaxies above 1.3. Beyond measuring the luminosity function, we could look at the global density of star formation, which is the y-axis here, versus redshift, and see that more luminous galaxies became progressively more important as you went out to higher redshift. And this is a fundamental shift in the thinking of how galaxies form that was led by Spitzer. And we now have measurements of this obscured star formation luminosity function out to redshifts of 3. This is an example of work done by Naveen Reddy. And the sum total of this is that we learned star formation peaked at a redshift of 2, and that the luminous galaxies were important in driving this peak. And so we now have to understand why is this the case. One of the key steps that Spitzer made to understanding this peak of star formation was discovering what's called the main sequence of star formation, which is essentially that there is a relation between the stellar mass of galaxies and the star formation rate of galaxies. And this evolves with redshift in that at a given stellar mass, galaxies have higher and higher star formation as you go to higher redshift. And this is now thought to be a fundamental property of galaxy evolution that's driving this. And it's only by having independent measurements of the star formation rate and the stellar mass that this was possible, and both of those measurements are driven by Spitzer. In the next few years, we're going to push this out to redshift of 10. We already have some measurements out to redshift of 8 using a combination of Spitzer and Hubble data. But we're now at the forefront of being able to push this out to the highest redshifts that are currently measurable. Beyond measuring star formation, Spitzer was able to separate the star formation in galaxies from the active galactic nuclei, or AGN, that are thought to co-evolve with the galaxies. And these are examples of two famous diagrams, one by Mark Lacey, another by Dan Stern, that select active galactic nuclei using Spitzer data. And similar concepts have been shown to work out to redshifts beyond 4 to measure the quasar luminosity function. This work that we did with Dan Masters, and have been proposed to work out to even higher redshift. And so in the near future, we'll be using this to push to find black holes with Spitzers out to the highest redshifts in the observable universe. When Spitzer was in its cryogenic phase, not only could they find the AGN, but we could cleanly separate the emission from active galactic nuclei from the star formation. And this is examples of spectra taken from the 5 Muses survey from Wu et al., showing emission from pure AGN here in red, going to pure star formation in green. And the fact that you can decompose these spectra into different components and understand what fraction of the infrared luminosity or total luminosity of the galaxy is coming from star formation, what fraction is coming from active galactic nuclei. This was done systematically in a legacy survey in the Cosmos survey. This is a paper by Fu et al., who was able to decompose the infrared luminosity function into galactic and or to star formation and black hole components, and understand what fraction of the coevolution came from stars and what came from active galactic nuclei. And this was used out as far as redshift of 4 by Rikers et al. To show that very luminous infrared systems at redshift of 4 were actually dominated by star formation rather than black hole accretion. One of the key things that Spitzer did was measure the stellar mass density of the universe. And this fundamentally requires rest frame data at greater than 0.5 microns. And this was very difficult to obtain, at redshifts greater than 1 before Spitzer. I'm showing work here by Mark Dickinson that was published in the year that Spitzer was launched, using the B-band luminosity function as a proxy for stellar mass. And you can see how uncertain this is, and how those uncertainties translate into large uncertainties in the global mass density evolution of the universe here. And it's very difficult to differentiate between different models of mass accumulation in the universe. Now we have excellent measurements of the stellar mass function and stellar mass density of the universe, not only by overall galaxy mass, but also as a function of galaxy type. This is work showing by Hilbert et al., showing the difference between the mass function of star-forming and quiescent galaxies. And on the bottom here is the fractional error, and you can see it's dominated by cosmic variance. And the measurement is fundamentally limited by the area of Spitzer data that we have, rather than measurement uncertainty. And this has been pushed out to redshift of 5. This is work by Lee et al. In the Goods fields. And again, it's dominated on the bright end by lack of sufficient area of deep Spitzer data. And here we see we can now measure the global mass density evolution of the universe for star-forming and quiescent galaxies, shown in green and red respectively here. And you can see we have very tight constraints that are typically smaller than the model errors. And we're going to use this in the future to link star formation, or use this in the future to be able to link dark matter and star formation with clustering. I'll show some of that in the future. So we have measurements now of the global stellar mass density out to redshift of 8 with Spitzer, and soon we're going to have measurements out to redshift of 10 using gravitational lensing with the HST frontier fields and other lensing. This is some examples from Bowens et al. And Ko et al. Of high-redshift galaxies. And actually, just today, or I guess last week now, we have a redshift 10 redshift 10 candidates galaxies in the Goods North field that'll enable us to start measuring the stellar mass density out at these very high redshifts. Beyond measuring the stellar mass, we're also able to learn something about the individual galaxies. Looking at the broad spectral range that Spitzer enables out to the mid-infrared, we're able to learn that redshift of 4 galaxies are fundamentally different from local galaxies. They have much stronger emission lines, and they're much younger and have much lower metallicities. And you can see here two sets of SED fits. The top is without emissions lines, the bottom is with emission lines. The emission line fits fit the data much better. Looking at it in another way, we can look at redshift versus the 3.6 to 4.5 or channel 1 to 2 flux ratio. And you can see the gray shaded region here is the region allowed by stellar synthesis models for galaxies. The solid lines show tracks of different types of quasars or AGN. And you can see there's a clear excess of galaxies that have much stronger emission, indicating the presence of strong emission lines in the spectra. And these are all spectroscopic redshifts, and so it's pretty reasonably conclusive evidence that there are these very strong emission lines from young metal poor galaxies at high redshift. Since Spitzer is so sensitive to stellar mass, it's also sensitive to concentrations of stellar mass. And so it can see the most massive structures out to very high redshifts. And we've now discovered virialized structures out to redshift of 2 using Spitzer, using Gatto et al. And this is a particularly prominent example I'm showing from Broadwin et al. At redshift 1.75. That's an extremely massive cluster. And the number density of these clusters can be used to constrain cosmology because only so many of these massive structures are able to form given cosmology in the universe. We're also able to see these very massive structures before they virialize with protoclusters, and we've now found protoclusters out to redshifts of 6 and possibly beyond. And Spitzer is essential for this because it conclusively shows these clusters are massive rather than just concentrations of star-forming galaxies. This is an example that I found in the Cosmos field, and here we see the cluster core of 6 galaxies. And this is within the radius that will emerge to eventually form a CD galaxy. And we can show with Spitzer that there's enough mass here mass and here that these will eventually form a massive CD-like galaxies. We're going to find many, many more of these with the data that's been collected by Spitzer in cycle 8, 9, and 10. So what are we going to do in the next 10 years with Spitzer? We're going to find tens of galaxies at redshift of 8 to 10, possibly many more. And we'll be able to understand what is the stellar mass density and stellar mass function of the early universe, and hence how did the first galaxies form and what is the processes dominating those first epochs of galaxy formation. We're also going to be able to link the stellar mass density of the universe to the stellar mass in the universe to the dark matter out to about redshift of 7 using clustering measurements. And so this is just an example of this, showing the stellar mass density versus the halo mass, alternatively the stellar mass over the halo mass ratio as a function of halo mass, and you can see that the ratio peaks at halo mass is around 10 to the 12. We can split this up by star formation and look at how the star formation efficiency peaks at different redshifts. So it's the same, the color coding is the same on the bottom and top panels. And you can see the star formation is preferentially peaking in group-like environments at redshifts of 1.2 or 1.15, but is preferentially in the field at redshifts of 0.1. And you see this fundamental shift from the higher density environments to lower density environments that's expected from biased galaxy formation. And we're going to be able to push these measurements out to significantly higher redshift with deep wide field surveys with Spitzer. Also, if we do very wide field surveys with Spitzer, we're going to be able to search for the highest redshift quasars out to redshifts of 7 to 10. And so this is just an example of work that was done by Robertson et al. 2007, suggesting different ways of selecting high redshift quasars and the amount of area that you need to find them. And you can see you should be able to find redshift 7 to 10 quasars, or the progenitors of more massive galaxies at low redshift, with roughly 400 square degrees of Spitzer data, which already exists in the archive. And if you use Spitzer data to select it, so you have a lower efficiency, we would need to get this we'd need to get about 1,000 square degrees to 24th magnitude, which is possible if we spend a significant amount of time with Spitzer. And this is something fundamentally JWST won't be able to do because it can't cover these large areas. So just to summarize, let's hope for another 10 years of Spitzer so we can continue doing these exciting things at the frontiers of the universe. And that's it.